I've drawn another pair of axes down below our Q versus T graph, and this is for our current. What we're going to do is take a look at this graph of Q versus T and see if we can figure out what is the slope of that graph at a bunch of different points, and see if we can use those to figure out what must the current be. Remember, the slope of a graph is the slope of a tangent line to that graph. So let's pick this point right up here at the peak of our sine wave. A tangent to that would be a horizontal line. What's the slope of a horizontal line? It's 0. That means the current must be 0 at that point, at that time. What about down here? The minimum of our sine wave. Again, a tangent would be horizontal. The slope must be 0 again. So right in the center here, 0. Again, up here, the tangent has 0 slope, so 0 current. Down here, again, tangent is horizontal, 0 slope, 0 current. Now, what about this point over here? What's the slope there? Well, we know the sine wave continues here. The slope would look something like that. Some positive number. We're not sure exactly what that number is, but let's notice it is positive, and it's the maximum positive value that any point on the curve will have. So that's going to be where the current is positive and maximum. We're not sure what the value is, but I'll just draw this in as some positive value. And let's remember, that's going to be our maximum current. What about over here? What about that point there? Well, notice the slope there is negative. And likewise, it's the largest negative value. There are no other larger negative values. Up here, the slope is less. Down here, the slope is less. They're negative, but still less than the maximum value here. And that negative value is going to be the negative of this positive value. So we know that whatever that current is, we don't know what the value is, but it's going to be the same distance below the axis as this one is above. And then likewise over here, what do we get? Well, the same positive maximum value. Over here, we get the same negative maximum value. There we go, something like that. And then one more over here, positive maximum value. There we go. What does the current look like? Well, we'll join these points up with a smooth line. What do we end up with? Something that looks like this. Very good. What do we get? What does that look like? Well, it looks like a cosine curve. So we know that the current is going to look like cosine something, some cosine time dependence. But also notice the wavelength of this is the same as the wavelength of this. The frequency of this curve has to be the same as the frequency of this curve. So we know that the cosine time dependence must be cos omega t, the same frequency as the charge. Well, what about the amplitude? Well, we're not sure, but we know that we could write this as, say, some amplitude I naught. So we know that the current has a form of I naught cos omega t. The only thing we don't know yet is what is I naught. Let's use some physical arguments about capacitors and see if we can't figure out what that I naught is going to be. We can imagine that if we increase our voltage amplitude, what do we think would happen to the current? Well, if we increase the voltage amplitude, that means rather than pushing a little bit, we're pushing harder on the circuit. What would we expect to happen to the current? Well, we would expect the current to increase. If we push harder, we would expect to get more current through our circuit. If we double the voltage amplitude, we would expect to get twice as much current. That seems to make sense. Well, if we double V naught, we would then expect to double I naught. Double the applied voltage, double the current responding. So we might write an equation that shows that proportionality, and we might say that V naught is proportional to or equal to something times I naught. But what should we put in here? Well, V equals something times I. Oh, you think maybe we should put in the resistance here. V equals Ri. But this is not a resistor, it's something else, it's a capacitor. We cannot put a resistance in there because we don't have a resistor. We need to put in something else. What are we going to put? Well, let's just call it X. We don't know what it is yet, but we'll figure it out. This quantity is actually what we call the reactance of the capacitor. And just looking ahead, just a little bit later, we're actually going to have another reactance. So to specify that this reactance is for a capacitor, I'll put a little subscript C here, and this is then X sub C. We call this the capacitive, reactance. The capacitive reactance. It's not a resistance, although it kind of looks like a resistance in this equation. V equals Ri, or V equals Xi. It looks like a resistance, and as a matter of fact, because of the similarity in equations, the units of capacitive reactance are the same as the units of resistance, which are ohms. So the units of capacitive reactance are ohms. Very, very good. Well, we've taken one more step. We can figure out I naught if we knew X sub C. What is X sub C? Let's make some arguments, some physical arguments about capacitors, and see if we can't figure out at least some things that might affect the capacitive reactance. Let's remember what C tells us. Q equals CV. So if we have a voltage source of, let's just go back to DC currents for a second, of 1 volt. C tells us how many coulombs will fit, so to speak, on that capacitor for 1 volt. Or you might say it tells us the number of coulombs per volt that will fit on the capacitor. If you have, say, a capacitor of 1 farad and you apply a voltage of 1 volt, you will fit 1 coulomb on it. If you have a capacitance of 2 farads, you would fit 2 coulombs per volt. If you had a capacitance of 10 farads, you would fit 10 coulombs per volt. So the capacitance tells us, so to speak, the capacity of the capacitor, how much charge per volt fits on the capacitor. How will that affect this result if we change the capacitance? Well, let's imagine that these two plates of the capacitor have a capacity described by the capacitance like, say, 2 glasses. How much 2 glasses can hold? Small glasses would be like a small capacitor. Large glasses would be like a larger capacitor, being able to hold more fluid or more charge per volt, so to speak. Now, how might that affect the current in this circuit? Well, let's imagine we have a frequency of our circuit of, let's say, 1 hertz, 1 cycle per second. And imagine we have a small capacitor. As the circuit goes back and forth, positive and negative, that's like taking the liquid in these glasses and pouring them back and forth 1 time per second. The current sloshing back and forth from plate to plate, 1 time per second. So just imagine how much fluid would this be if I were to do this once per second. And now imagine that rather than a small glass, I have large glasses. And I pour these back and forth once per second. Am I going to end up pouring more fluid or less fluid with the larger glasses? More fluid. Once per second, I've got to empty out these glasses once per second. Rather than the smaller glasses, I've got to be pouring more fluid per second. More fluid per second means more current. So, by increasing the capacitance, I need to increase the amount of current, the current amplitude. Well, let's write that down. If I increase the capacitance, that means I must increase the current amplitude. For this equation, for a constant voltage amplitude, if I increase I, what must I do to XC to keep the product the same? If I increase this side, I have to decrease this side. That means XC must decrease. When I increase the capacitance, the capacitive reactance must decrease. Very interesting. Let's think about one more thing. What about the frequency? Could the frequency have any effect on this? Well, let's go back to our capacitor, our glasses. Now, let's imagine that I've got these full of, or one side full of liquid again, and I pour this back and forth once per second. Think about how much fluid is going to be flowing. But now, rather than once per second, let's imagine I do this 5 times per second. And I've got to slosh this back and forth 5 times per second. Am I going to be moving more fluid when I do it fast? Yes, I'm going to have 5 times the amount of fluid flowing per second than I do if I'm doing it slowly. So by increasing the frequency, I must increase the current. I must increase how much current is sloshing back and forth. So if I increase omega, again I must increase the current amplitude. Again, increasing the current amplitude must mean I decrease the capacitive reactance. So X sub C must decrease. Very good. It turns out that these are the only 2 things, the capacitance and the frequency, that the capacitive reactance depends on. So we can actually write this as an equality. I'll put it up here. X sub C must decrease with increasing capacitance and decrease with increasing frequency, and so it turns out that X sub C is equal to 1 over omega C. Very, very good. Let me just put down a recap of what we've found here. What we have is for an AC voltage source, V equals V naught sine omega t, with a capacitor with capacitance C, the applied voltage amplitude, V naught, is proportional to the current amplitude I naught by the equation V naught equals XC I naught, where XC is what we call the capacitive reactance and has a value of 1 over omega C. Notice that this looks very, very much like Ohm's law. However, we don't have a resistor in here. It's the capacitive reactance. We could, again, divide both sides by the square root of 2 and write this in terms of the RMS values. VRMS equals XC times IRMS. One more thing I want us to keep in mind, and that is back here, when we figured out what the current was, and that the current had a form of I naught cos omega t. What I want us to notice is, now the charge, this is very much like it's in phase with the voltage. So we can think about this as the phase of the voltage as well as the charge. Notice that we hit the peak of the current before we hit the peak of the voltage. So in this case, if this is the voltage and the voltage is going up and down, again the current is going up and down, but the current is up before the voltage is up, so that the current leads the voltage. It's always ahead of the voltage by how much? By a quarter of the entire oscillation, a quarter of a phase. Very good, we'll come back to that, but let's just keep in mind, what did we see for the resistor? For the resistor, the current and the voltage were in phase. For the capacitor, the current leads the voltage. It's ahead of the voltage. Very, very good. Now, let's take a look at one more circuit element that I mentioned before, the inductor.